Guided problem solving number 1. Consider a steam power plant operating on the ideal Rankine cycle. Steam enters the turbine at 300 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. If the isentropic efficiency of the turbine is 87% and the isentropic efficiency of the pump is 85%, determine the thermal efficiency of the cycle. The net power output of the plant for a mass flow rate of 15 kg per second and the cooling water flow rate in the condenser if cooling water enters at 20 degrees Celsius and leaves at 35 degrees Celsius. Compare the thermal efficiency to the efficiency of ideal Rankine cycle. So we're given with a cycle that operates between a pressure of 3 megapascal and 10 kilopascal. And then the steam enters the turbine at 350 degrees Celsius. So the isentropic efficiency of the turbine is 0.87, and for the compressor that is 0.85%. We're also given with the mass flow rate of 15 kg per second and the temperature of the cooling water used in the condenser. So that's 20 degrees Celsius inlet condition and 35 degrees Celsius outlet condition. We're going to tabulate the properties at the different points, assuming that the process is still ideal. So we're given with the pressure at point 1 as 10 kPa. So we have here 10 kPa, and then the pressure at point 2 is 3000 kPa. So this is a constant pressure line here, that's why it's 3000 kPa. Same also with point 3 and point 4S. So I name it 2S and 4S to denote that these are the isentropic processes. 2S and then we have the 4S. 4A and 2A represent the deviation from the ideal. So this is the actual. So the actual path is kaning na broken line. Using our software, inputting saturated liquid at 10 kPa, our temperature, entropy, quality, and enthalpy are as follows. So since process 2 to 3, 1 to 2 is isentropic process, so they have the same entropy. And then using specified state points for the subcooled liquid region, so inputting 3000 kPa and entropy of 0.6492, our temperature and enthalpy are as follows. So as you can see, there is an increase of temperature after the pumping. At point 3, since the pressure and the temperature are given, then we're going to use the same specified state points in the software, inputting 3000 and 623.15 Kelvin. Then our entropy is 6.7449 and the enthalpy is 3116.1. And then process 3 to 4 is isentropic process. So 3, 4S is isentropic process. That's why they have the same entropy. So inputting 10 kPa and 6.7449 in our specified state points. Then our temperature is 318.96 and enthalpy is 2136.1. So we're able to get all of the properties that we will need to compute the different quantities. So the first unknown is the thermal efficiency of the actual cycle. So take note that the actual cycle is represented by 3, 4A, 1, and 2A. So this is the deviation from the ideal cycle. So the thermal efficiency can be computed using the formula work of the turbine minus work of the pump over Q in. So for the work of the turbine, that is the change of enthalpy across the turbine. And since we are considering the actual cycle, so that is H3 minus H4A. So this is 3 to 4A is the turbine, represents the turbine. So we have H3 minus H4A here, minus work of the pump. So same also, we're using the actual, so that's why we have 2A minus 1. So H2A minus 1. And for the heat input, that is at the boiler, so that's H3 minus H2A. So H3 minus H2A, that's why we have here H3 minus H2A. So that is the thermal efficiency for the actual cycle. We're going to use the actual points. Since we do not yet have the actual value of enthalpy at 0.4 and 0.2, we're going to calculate that first. For the actual enthalpy H4A, we can get that from the formula. The turbine isentropic efficiency of the turbine is H3 minus H4A over H3 minus H4S. And since we already get H3 and H4S in the table, and then since our isentropic efficiency of the turbine is given, then you have to substitute all of that so that our only unknown is the H4A. So our H4A, or the actual enthalpy at 0.4, is 2263.5. So this is the actual enthalpy at 0.4. As you can see, this is higher than the entropy here in the table. So that is the deviation. For the enthalpy H2A, we can use the isentropic efficiency of the pump. And then from the given, the isentropic efficiency of the pump is 0.85. So substituting from the table the value of H2S and H1, so that's why we have this, and then our only unknown is the H2A. So our H2A is 195.36 kilojoules per kilogram. As you can see, that is also different from the ideal, which is 194.83. So there is also a deviation at 0.2. And since we already have H2A and H4A, and then for H3, we can get that from the table as well as H1, then by substitution of those values, our thermal efficiency is 0.2907 or 29.07%. So the thermal efficiency tells us that only 29% is actually converted to useful work. And then the remaining is lost. The second unknown is the net power output of the plant for a mass flow rate of 15 kilograms per second. So the net power output can be computed using mass flow rate times the work of the turbine minus work of the pump. So that's the net work. So we are going to use still the actual value of the enthalpy at 0.4 and 0.2. So our value is already calculated and tabulated. That's why our work net, if we're going to substitute the 15 kilogram per second mass flow rate and the enthalpy, our work net is 12,735.75 kilowatt, or that is 12.7 megawatt. So the power output of the power plant is around 12.7 megawatt. T, the cooling water flow rate in the condenser if the cooling water enters it at 20 degrees Celsius and leaves at 35 degrees Celsius. So again, the condenser is used to cool the steam, the working fluid of our cycle. So this water may come from the river or from a well. So that's why we have, as you can see, it increased its temperature because at the condenser, it's actually hot before entering the condenser. And then it has to be cooled back to 0.1. That's why our cooling water will increase its temperature. So by energy balance in the condenser, so for us to lower the temperature at the condenser from 0.48 to 1, then we need to introduce here, we need to introduce a cooling water. So there's actually a heat loss here. So that's our Q out. So our heat by energy balance, the heat by absorbed by the cooling water is equals to the heat that is rejected here. This is actually Q out. So at this process 4A to 4. So this is the condenser side. So that's why we have, so for the cooling water, we can compute the heat as mass of the cooling water times the specific heat of cooling water times the change of temperature of the cooling water equals to the Q output here in the condenser, heat rejected by the condenser. So that is H3 minus H2A. Condenser boiler. Okay. H4A. Two to 60. Letter C. The cooling water flow rate in the condenser if the cooling water enters at 20 degrees Celsius and leaves at 35 degrees Celsius. By doing an energy balance in the condenser, so our condenser is here, we can see that there is a heat rejection at the condenser. So this heat rejection happened because of the cooling water. So we have here a cooling water which is at 20 degrees Celsius, and it exchanged heat with the hot fluid from the exit of the turbine before entering the condenser. While entering the condenser, it exchanged heat with that working fluid. That's why it increases to 35 degrees Celsius. So as a result of that heat exchange, our steam, so our working fluid in the cycle, decreases its temperature, but the cooling water increases. So since we only have two heat interactions here, then we can create an energy balance in the condenser as the heat absorbed by the cooling water is equal to the heat rejected by the condenser. So for the heat absorbed by the cooling water, we can write that as mass of the cooling water times the specific heat times the delta T of the cooling water, and that is equal to the heat rejected by the condenser, which is equal to mass flow rate times the change of enthalpy across the condenser, that is H4A minus H1. So that's why we have this one here. So by substituting the value, so our unknown, which is the mass of the cooling water times the specific heat of water multiplied by the temperature difference of the cooling water, and that is equals to the heat rejected by the condenser. So we can get this one from our actual enthalpy at point 4 and then the table value of H1. So our mass of the cooling water that we are using to cool the working fluid is 494.79 kilogram per second. So that's an enormous amount of energy. So 494 kilogram per second. Letter D. Comparison of thermal efficiency to the ideal Rankine cycle. So for the ideal thermal efficiency, we can simply use the value of the isotropic values, which is H4S and the H2S we can get in the table, but the same formula. So by substituting those values, our ideal Rankine cycle efficiency is 33.44%. So as you can see, based on the result, the thermal efficiency of the actual, which is 29.07%, is lower than the ideal cycle, which is 33.44%. So the general effect of the deviation from the ideal cycle is a decrease in the thermal efficiency. So we need to find ways to reduce the deviation by reducing or eliminating the irreversibilities due to heat loss and fluid frictions. So that is how to analyze the actual Rankine cycle.